Okay, like before, there are 3 steps involved. One is we need to initialize a solution or a guess the solution. We need to figure out a search direction where to go next from that guess. And then when we keep doing that, we need a criteria which will terminate the algorithm. Okay, so let's talk about these 3 for Newton Raphson. So first, the initialization. Now, previously in secant and the bisection and bisection method and regular Farsi method, we had to get 2 guesses x1 and x2, and they needed to bracket the root, right? By bracketing, I mean the root should lie between, in this case, x1 and x2. That's bracketing the root. The good thing about Newton Raphson is that it only needs 1 guess. And so since it's only 1 guess, you don't really need to bracket anything. So just needs 1 guess. And the good thing is that you just can give a random guess and you should be fine. Now, it so happens that sometimes your guess is so far and the f of x is so complex that you do not end up with a solution. In that case, you need to give another guess and yet another guess till you try to get a solution. Okay, so this is a good thing about Newton Raphson. You don't have to sort of do extra work in the beginning to do anything like you would for bisection or regular Farsi, where you have to bracket the root. The second thing is the search direction, or where do you go from that guess. So bisection, it was the arithmetic mean. Secant method was we drew a straight line and found the intersection with the x-axis. This one is similar to the secant method, but with only 1 guess. So let's see how that goes. So here is, let's say, a graph of f of x, and let me choose the same function. So we chose a function which looks like this. Okay. So let's say that your initial guess is right here. Okay, let's call that x1. So this point here is going to be x1 for the x-axis and f of x1 for the y-axis. And clearly that is not a root, right? So what what Newton Raphson does is it draws a tangent line at this point. And as you can see that the tangent line intersects the x-axis at some point x2. In fact, the coordinate of this point is going to be x2 for the x-axis and 0 for the y-axis. So now we have to basically figure out what that x2 would be. So what we can do is we can write the equation of a straight line, that is that tangent. And so you can see that the slope of the line is f prime x1, right? So that's the, if you have a curve, and if you take the first derivative and evaluate the point at x1, that is the slope. But the slope can be found another way. We can actually use this line to find the slope. To find the slope, you take the difference between the y coordinates of those 2 points. So here the y coordinate is f of x1. The y coordinate here is 0, divided by the x coordinate of the first point, so x1, minus the x coordinate of the second point. So that's also another way of figuring out the slope. So now what we do is we solve for x2. I think you get x1 minus and that would be how you go about figuring out point x2. So you need f of x, you need the rate of change of f of x, or the slope. So in this particular example, what would be done is, okay, so we found compute x2. This is this point. Once you find x2, you do the same process all over again. You just draw a tangent here. This will be x3. And then the tangent again, and so on, right? With the tangent. It just keeps going. You can see that you start going closer and closer to the point, which is the root, which is this one. So x1 is further away from the root, the big red blob I drew, but x2 is closer, and x3 is even closer, and x4 is even closer. So you just start going to the root that way. And then the termination criteria is the same as before. Space here. Termination, same as bisection and regular falsy. That is, you use the tolerance of f of x, and you use the iterations if you're not converging fast enough. Okay, so let's put this into practice. We're going to solve the same problem with one guess instead of two, and then see where we get to. Compute the root of the function f of x equals x squared minus 3x using Newton Raphson method. Use an initial guess of 4. Okay, so we'll say compute 3 iterations by hand, and then write a computer code that will terminate when f of x is less than 1e negative 3. Okay, the same problem. I choose an easy problem because we know the solution to it. It's 0 and 3. And we've also done this using bisection. It took about 11 iterations and 8 iterations with the regular falsy. So this gives a nice benchmark to compare. Okay, so for Newton Raphson method, remember the formula is x2 equals x1 minus f of x1 divided by f dash x1. So we would need f of x, right? So f of x is x squared minus 3x, and we need f prime of x, which is 2x minus 3. Okay, with that, we are ready to start. Iteration 1. Okay, so we know that x1 is 4. That's given to us. Let's write here 4. So f of x1 is 4 square minus 3 times 4 equals 4, and f dash of x1, which is 2x minus 3. So 2 times 4 minus 3 equals 5. So x2 is x1 minus f of x1 divided by f of x1 prime. X1 is 4, f of x1 is 4, x prime is 5. So 4 minus, I think, 0.8. So 3.2. That's 3.2. Okay, remember root is 3 and 0, so it's getting closer to 3, looks like. So we did this. We have to still check for convergence, okay, every step. So we check f of x2, which is 3.2 square minus 3 times 3.2, which is, I got 0.64, which is greater than 1 e negative 3. So we have not converged to the solution. It's not small enough that we can stop. Okay, let's keep going. So we have 3.2 as our next guess. So what we'll do is we'll put x1 equals x2 equals 3.2. So now we start with the same process with 3.2. That's the initial guess. Okay. Iteration 2, x1 is 3.2. F of x1 is 3.2 square minus 3 times 3.2. And I think we computed that to be 0.64. Okay. F dash of x1 is 2 times 3.2 minus 3. I think that comes out to be 6.4 minus 3, so 3.4. Okay, we all set to compute x2. It's x1 minus f of x1 divided by f prime of x1. So x1 is 3.2 minus f of x1 divided by 3.4. Okay, so I don't know if you computed, you can check this answer. It's 3.011. That's what I got. Okay. Okay, so we got 3.011, but we always check if we have to stop or we have to keep continuing. So for that, I compute f of x2, which is 3.011 square minus 3 times 3.011. Turns out that this is 0.033, which is greater than 1 e negative 3. What is 1 e negative 3? It's 0.001, right? So clearly, 0.0330. So we are close. We know that solution is 3. Maybe we'll find it in iteration 3. Okay, so we still have to continue. So we do third iteration. So now my x1 is the old x2, which is 3.011. And then let's do final iteration 3. That was what we were asked to do by hand. Just take it on a new page. Okay, so iteration 3. Okay, x2, sorry, we want f of x1. Okay, the good thing is we already computed that. It's from the previous page, it is 0.033. So I'm just going to use that. And then f dash of x1 is 2 times x, so 3.011 minus 3. So this is 3.022. Okay, so we all set to compute x2, which is going to be x1 minus f of x1 divided by f dash x1 3.011 minus 0.033 divided by 3.022. Okay, it comes out to be so x2 is 3.1234. 1, 2, 3, 4, 8. Wow, it's so close to 3. So we need to check the conversions. F of x2 is 3.00008 square minus 3 times 3.00008 equals, so I actually get 0.002, which is also equal to 2 times 10 raised to negative 4, right? Or 1e negative 4. Okay, which is clearly smaller than 1e negative 3. Okay, so what we've seen here is this method actually converged in just 3 iterations. Okay, and we could actually find the solution by hand. Just 3 iterations compared to 11 iterations for bisection and 8 iterations for regular falsy. Okay, so that is in fact the root. The root is okay, so note that the method got the root accurate to like 5 decimal places, right? The actual root is 3.00000, but it gave you 0.00008, and that is because of 1e negative 3. If you said you want to go 1e negative 6, it'll actually give you 0.006, 5 zeros, and then maybe some number. Okay, so it just depends on when you decide to call it a day and stop your conversions. Okay. Any questions on this? Okay, so now that we have this, let's write a code and see if we can get the same solution, or rather check our solution with computer code. Okay, so the first time I did this with bisection, I used ChatGPT. The second time I wrote code for regular falsy, I used the bisection code to write to update my code for regular falsy. This time I'll just write code by myself without using ChatGPT. Okay, and I think that the best way to start is to look at the code which ChatGPT gave for my main, the bisection method. So I'm going to open these two just to help me with some things. Like I don't want to write all of this all over again. So, but I'll write the code myself. So let's open a new script. We notice that, let's look at the main. This is the driver file. This basically will drive the simulation, the code, right? So we can just copy paste this, but then modify this bisection to something we write for Newton Raphson. So let's take this and then save it as let's see. Numerical methods. Let's make a new folder called Newton Raphson, and then call it main Newton. Okay, now let's do it one at a time. So let's see what we have is we have the function f. We have initial lower and upper bound, but we don't really need two guesses, right? We just need one guess, and that is in this case going to be b equals 4. So let's just keep that. Let's eliminate this. The tolerance is fine. Max iterate is fine. What I want to do here is delete this. What I want to be able to do here is call this Newton Raphson. So I need to write that function, which will take as inputs f, a, b. Well, I don't have a, so let me get rid of that. Tolerance, max iterate. Now it turns out that I need something else for this method, right? I need f and df dx, or the derivative of f. So let me define that. Dx equals at x. So the derivative of x squared minus 3x is 2 times x minus 3. Okay, so here what I'll do is, instead of having the second argument, I'll pass df dx. Okay, if you like, it's better to call it a, I think. Okay, so now we are left with creating that function Newton Raphson. So let's take this, create a new file, and call it function root Newton Raphson. So I'm doing this because once I do that and the path is added, I can do Control S, and it opens the same folder which I wanted to save it. Okay. So remember to save this file in the same folder, otherwise it will not run. Okay. So now what do we do? Well, clearly we have a method to update the search direction, and then we want it to run continuously. So there needs to be some kind of a loop which will keep trying to get new x2 based on x1, which is in this case going to be a. So I probably need a while loop, and then I need to end the while loop. So what we're going to do is, in the while loop, we're going to say that it's going to run till it hits a certain tolerance. So what is that value? Well, let's call fa as f of a. Okay, and then we know that in order to converge, we need apps f of fa, which is f of a, should be less than, it should be, so this loop will keep running till the condition inside the bracket is violated, right? So if this is the function, the value is greater than tol, okay, so for example, if apps f of a is 4 is greater than 1e negative 3. So if that's the case, then the loop will run the moment that condition is violated, which means that if abs f of a is 1e negative 6, which is smaller than tol, it's violated, it'll get out of that loop. So that's the right condition. Okay, so we got that. Now we know that there's an update. The update is something like x2 equals x1 minus fa, or f of x1 divided by df dx x1, right? So let's write this. I'm going to use b for, because there's a already, a minus f of a divided by tf tx. Okay. So what's happening is, initially, clearly f of a is going to be much greater than tolerance, so it will get in this loop. It'll compute b. When it computes b, it needs to then compute fb, f of b. Okay, now if it does that, there's going to be a problem, because the thing over here is always checks for f of a. So what I need to do is, I need to redefine the variables. So this is what it does every step, but I need to redefine a equal to b. That is because I'm only going to replace a with b for this check to go through. So that's the case. Then f of a will be fa will be f of a. So it will check that, and when this condition is satisfied, or that is, it is not satisfied, that is, it becomes smaller than tolerance, it'll basically come out, and then I need to return the root, which is the solution. So I'll say root equals a, right? Okay, let's try this. So here it is, root is 3. Didn't require much of coding, right? Now, there's some other things I would like to know. I would like to know the number of iterations it needs, but there's nothing in my code which keeps track of the iterations. So let me do that. Iterations equals, or iter equals 0. So every time it does this computation, I update the iter. Okay, and then maybe I want to print it. Just will this work? Let's see if this works. So when it finishes this, it should probably print this. Let's see if that works. Yeah, so you see this iteration equals nothing. It turns out that the reason why that's going on is because this is a string, and then this is a number, and you can't combine a string with a number, so you need to convert that to string. And I think at least this is how I would do it in MATLAB. I take a number and convert it to string. Now, if you're always in doubt, you can always try this out like this. Iter equals 4, and then take this, put it here, and say it prints fine. So that really worked. If you want documentation, you just say help num to string. Now, I don't know if this will work definitely in MATLAB, but I don't know if the documentation Octave is good enough to give me the yeah, it just says go to the internet. But if you go to the internet and search for num2 str, it'll tell you. You can also, for that matter, look at MATLAB documentation. They've actually taken many of the MATLAB functions, the function names, and just use them in Octave. So it's really transferable. Okay, so I think this will work. Let's run this. Okay, so iteration is 3, root is 3.000. What I would like to do now is we would like to see the progress of this solution every iteration. And instead of reinventing the wheel, what I'm going to do is I'm just going to look at how it was done by section. This was ChatGPT generated code. It basically did this display. So let me just take this and just modify it to suit my progress, the progress here. So it should be in the while loop, which I'll do. Let's go here, maybe here. So iteration. So we already have iteration. A, we already have A. Here, B doesn't make sense. There's just one guess, A, and then there's f of x. So let's just get rid of this. Let's get off C, but maybe we want to show f of A. So maybe f of A equals f of A. And then I don't think we need anything else. You need to be careful. There's so many things floating here that if you make a mistake, it's not restaurant. So I think there's a bracket which needs to close. I think this should work. So main Newton Raphson. So yeah, so it goes to the same problem, which is it just doesn't print everything. Okay, so I already have this code, luckily. So this is basically create a diary with the file name output.txt. Whatever is written here will be saved to that file, and then there'll be diary will be off. Let me just comment this for a second. Run this. Well, now it just printed. Okay, but we also have it here. So if you go to, this is not the one, this is by section. If you go to Newton Raphson, here is the output. Okay, it's saved. Oh, it was just running on the background. Okay. So to prevent this, so every time you run the code, it copies it, but doesn't erase the previous stuff. What you do is you put a delete.output.txt, run this. And if you do that, not only is it printed here, it also is printed here. Yeah, there it is. So yeah, so you see that this is slightly differing from the way I solved it. Well, there's 3.011, I think that is right. But here I got 3.0008. I think it's because I did not carry the sufficient decimal places in my computation. At that point, you need to, if you want 3 decimal accuracy in the solution, at least my hand calculation, I need to carry 6 decimal places. So if you take 6 decimal places for f of a and then use that to compute iteration 3, you should actually get 3.008. So 3.0, like what I have is not very accurate. Okay. Anyway, for the exam, for all practical purposes, if you write usually 3 decimal places is good enough. Okay, so we got that. There's a couple of things I want to do with this code. We chose an initial guess of 4, and that gave us 3. The problem with this method is that, in fact, for any method we've talked so far, is that it only give you one root. If you bracket a root, it'll give you that root for bisection and regular falsy. In this case, it'll give you one root based on your initial guess. So for example, we know the second root at 0. So if you give close to 0, there's a good chance you'll get 0. So let's try -4. So here it took 5 iterations, and it gave me the root as -5.00018, okay, which is almost close to 0. Okay, so it gave me the other root. You could try maybe 10, which is further away. It took 5 iterations. If you try 100, it took 9 iterations, and it gave me the solution 3. You could try 1,000, and it took 12 iterations. Now, the code which is missing here is that the code which verifies if I reach a maximum iteration. If I reach a maximum iteration, it should just quit, right? So I can try to incorporate that. This is actually a good example. So if you have 1,000, we know that it basically takes more than 10 iterations. So why don't we test this code in this fashion? Let me make the max iter 10. I know this will not converge, right? In 12 iterations, in 10 iterations, it will not converge. So it should terminate the loop. It should tell me that it has not converged because maximum iterations reached, and that should be a complete code. So let me go and fix this. So I have this code. What I'm going to do is I need to check for basically this condition, max iter. So I go here, and what I can do is something as simple as this. If iter is greater than max iter, okay, so max iter is 10. So if I go to iter is 11 is greater than 10, all I want to do is this code should come out. And the way you can get a code to come out from the while loop is to put break. Okay, but it should also print a warning, right? So it should say this solution reached maximum iteration limit. Method reached maximum iteration limit. Solution may not be accurate. Okay. So let's see if this works. So here we go. We know for this case it should if it's all right, then it should tell me that warning. Let's go here. And you can see that after 11, it quit. It says maximum method reached maximum iteration solution in bracket, and it's 3.0064. So 3.064 is actually pretty close to 3, but it does do its job of printing that. Now, if I go back to 100 iterations, it should have no problem, right? With the code. So that basically means that what I've written there at least works for those two conditions. Now, you could try, this function is actually well behaved. I think even if you go a million, it will eventually converge. It's pretty powerful. It's actually quadratic. The convergence is quadratic. It takes 15 iterations. If you look at the one way of figuring out the convergence is to make a plot of the iteration versus f of x, and I think you will see it to be a curve, a quadratic, and then it's quadratic convergence. Okay, so this is working, and that's your code. So it was originally 4. Okay, any questions?